All right, let's dive in. Today, we're putting on our detective hats. Why? Because we're on the hunt for the math world's do not enter signs. You know, those sneaky little numbers that can make a perfectly good function just completely break down. We're talking crash, burn, the whole shebang.
Okay, you know the feeling, right? You're plugging away on your calculator, you think you've got it all figured out, and then bam, it just quits. Yeah, that screen. The dreaded error message. Well, guess what? That's not a glitch. It's not random. Your calculator is basically screaming at you that you just tried to break one of the fundamental laws of mathematics. And today, we're going to find out exactly what that law is. So that leads us right into our first mission, the denominator defense. It's all about learning how to guard our functions, how to protect them from the one thing that can bring them crashing down.
Okay, so to do that, we need to understand a super important idea called the domain. The easiest way to think about it, it's like the official guest list for a party. It's the complete list of all the safe numbers you can plug into a function. You know, the ones that won't show up and break all the furniture.
And the bouncer at this party, well, he's got one rule, just one, and it is non-negotiable. This is it, the golden rule, our prime directive. The denominator can never, ever be zero. Seriously, that's it. That's the big secret to this whole thing.
So our detective work is actually pretty straightforward. Our one and only job is to look at the denominator, that's the bottom part of the fraction, and figure out which numbers, which bad inputs, would make it turn into zero. Once we find them, we kick them out. They are not on the guest list.
Okay, so once we found our troublemakers, how do we actually write down the domain? Well, there are two main ways you'll see this. The first is called set notation. It looks kind of fancy, but all it's saying is, hey, x can be any number just as long as x doesn't equal 5. Simple. The other, which you'll probably use a lot more, is interval notation. Think of it like drawing on a number line. You're saying we can use everything from way down at negative infinity all the way up to 5, and then we pick back up right after 5 and go all the way to positive infinity. We're essentially just hopping right over that one bad number.
All right, theory's great, but let's get our hands dirty. It's time to solve a few case files. We'll start with a nice easy one and then ramp up the difficulty. So here we go, case file number 1, the obvious suspect. We need to find the domain for this function right here. Now remember, what's our one and only rule? We totally ignore the top. Our eyes go straight to the denominator, that 2x minus 8. And the process is just two quick steps. First, we take that denominator, 2x minus 8, and we make a statement. It cannot equal 0. Step 2, we just solve for x, like any other algebra problem. Add 8 to both sides, you get 2x cannot equal 8. Divide by 2, and there it is. We've got our culprit. X cannot be 4. That's the only number not on the guest list for this function. Nice work. Let's move on to case file number 2, the hidden accomplices. Okay, this one looks a little scarier, right? We've got a quadratic in the denominator. This means our bad numbers, our troublemakers, are a little more hidden. We're going to have to do some real detective work to find them. So what's the secret weapon here? It's factoring. We need to break that big quadratic down into its smaller parts. And when we do, that x squared plus 5x plus 6 becomes two simple pieces, x plus 3 times x plus 2. And just like that, we've unmasked our suspects. See, because those two pieces are multiplied together, if either one of them becomes 0, the whole thing goes to 0. So we just ask ourselves, what makes the first part, x plus 3, equal to 0? Well, that would be negative 3. And what about the second part, x plus 2? That becomes 0 if x is negative 2. And boom, we found them. Two bad inputs this time. X cannot equal negative 3, and x cannot equal negative 2. All right, detective, you're doing great. Time for the boss level. Case file number 3, the double agent. Now take a close look at this function. We've got a square root inside a denominator. This is a big deal, because now we have two different rules we have to follow at the same time. So here's the puzzle. First, we have the square root rule. We all know you can't take the square root of a negative number, right? So whatever is inside that root, in this case x minus 5, has to be 0 or bigger, so greater than or equal to 0. But then we have our good old denominator rule, the one we've been using all day, which says the entire denominator cannot be 0. You see the conflict here? The square root rule says equal to 0 is okay, but the denominator rule says no way it can't be 0. So which rule do we follow? Well, in math, when you have conflicting rules, the stricter one always wins. So we have to satisfy both. It can't be negative, and it can't be 0. So what's left? The stuff inside that x minus 5 has to be strictly greater than 0. And from there, it's easy. Just add 5 to both sides, and we find that x has to be greater than 5. Written in interval notation, that's parentheses, 5, comma, infinity, comma, parentheses. And take close attention to that round parenthesis next to the 5. That's super important. It means we get infinitely close to 5, but we don't actually include 5 itself. 5 is the line we can't cross. Fantastic. Now, before we close the casebook, let's talk about a couple of common traps, some false leads that trip up a lot of people when they're starting out. First and biggest one, the numerator. Just ignore it. Seriously. Unless there's a square root or some other problem up there, the top part of the fraction has absolutely nothing to do with the domain. It's a distraction. Second, that little U symbol we use in interval notation, that stands for union. It's just a way of gluing together the different safe zones. It means an x value is allowed if it's in this first part or in the second part. Okay, so at this point, you might be thinking, all right, this is a fun little math puzzle, but so what? Why does any of this actually matter? Well, it turns out understanding where the math breaks is one of the most powerful tools we have for predicting where the universe breaks. Let's look at something from physics called Coulomb's law. It's a formula that tells us the force between two charged particles, like two tiny electrons. And just look at it. The force is related to 1 over r squared, where r is the distance between them. See that r in the denominator? That should look very familiar. So let's ask the exact same question we've been asking all along. What happens to that force if the distance, r, between those two electrons gets smaller and smaller and closer to 0? Just like in our homework problems, as that denominator gets tiny, the whole thing just explodes. The force between them becomes infinite. Now, in physics, that's not just a math error. It has a name. It's called a singularity. It's a point where the forces are so extreme that the laws of physics as we know them just stop working. They completely break down. And the amazing part? The simple math we just learned, finding that one forbidden number in the domain, that's exactly how scientists predict where these cosmic breaking points will be. And that's what I want to leave you with. Think about it. The math itself told us exactly where it was going to fail. It flagged its own breaking point. So it makes you wonder, right? If a simple rule about division can predict something as wild as a singularity, what other secrets about the limits of our universe are hiding inside the rules of mathematics?